In the last lecture, we were considering finding out the inverse Laplace transform through the method of partial fraction expansion. We shall continue this discussion with an example. Let us consider f of s, a rational function which is s plus 2 over s plus 1 plus s squared plus s plus 1. This has obviously 3 poles, one at minus 1 and a pair of complex conjugate poles at minus half plus or minus j root 3 upon 2. So, one way of handling this would be to make the partial fraction expansion corresponding to the 3 poles. So, k2 over s plus half plus j root 3 upon 2 and another term corresponding to the conjugate pole minus j root 3 upon 2. Now, it turns out since this pole is complex, this will also be a complex number. K2 is a complex number, and since this pole is the complex conjugate of this, it turns out that K3 will be K2 conjugate. So, one way of handling this would be to find out the 3 residues corresponding to the 3 poles, find K1 which is simple, K2 which is of course complex, and K3 we do not have to spend extra time to find out K3, because once you know K2, the K3 will be K2 conjugate provided the coefficients in the rational function, coefficients of various powers of s in the rational function are real. So, in making this partial fraction expansion, once you find K2, K3 can be immediately found out. But then this needs a little bit of complex algebra manipulation. An alternative way of doing this would be to combine these 2 terms and get the result as a fraction, because after all finally when you find the inverse Laplace transformation, you will find out that when you have a function quadratic factor in the denominator, it is convenient to identify this with the Laplace transform of e to the power of minus alpha t cos omega t type of function. So, to do that, let us write this partial fraction expansion as say s plus 1 corresponding to k1, and the second term would be the combination of these 2. It turns out that will be s plus half whole squared plus root 3 upon 2 whole square. So, if we can express this quadratic factor in this form, it will be convenient because we can associate this with a well known time function, as we will see as we go along. Now, to find out the residue of the pole at s equals minus 1, you multiply this by s plus 1 and substitute s equals minus 1 in the usual manner, and you will get the result as 1. And once you have that, to find out the term corresponding to the numerator here, you can arrive at a common denominator and identify the numerator coefficients with the coefficients of s plus 2 and find out the numerator here as minus s plus 1. So, this is straightforward. I will not work out give the complete details. After having done this, you recall that the Laplace transform of s plus alpha over s plus alpha whole square plus omega squared, that is inverse Laplace transform of that is e power minus alpha t cos omega t. Therefore, we should like to express this as a linear combination of s plus half one term and root 3 by 2 as the other term. If we do that, then we can identify this with the Laplace transform of terms like e power minus alpha t cos omega t and e to the power minus alpha t sin omega t. So, to do that, let me write 1 over s plus 1 all right, and the second term s plus half whole squared plus root 3 upon 2 whole squared. Now, I must express this as a linear combination of 2 terms like this. So, since there is a minus s here, so I will write it minus of s plus half, that is we can recognize this to be the Laplace transform of e power minus half t cos root 3 upon t 2t with a minus sign out in front, but we have minus s plus 1. Therefore, instead of plus 1 you have minus half, therefore, you must introduce plus 3 by 2, but we must express this as a coefficient times root 3 upon 2. Therefore, this will be root 3 upon 2 multiplied by root 3. So, that is the linear combination of these 2 terms that we are looking for. Now, we have got the 3 terms which are known Laplace transforms of particular time functions. Therefore, we can find out the inverse Laplace transform, that is the time function as corresponding to the first term you have e power minus t, corresponding to this term you have minus e power minus t upon 2 cos root 3 upon 2 t, and corresponding to this term you have plus root 3 e power minus t upon 2 sine root 3 upon 2 t. So that is the, of course, the whole thing is multiplied by u of t. So that is the inverse Laplace transform of this given rational function. So now we have used here a trick in the sense that we have not found out the residues of all the poles specifically. Whenever you have complex conjugate poles, a pair of complex conjugate poles, it would be convenient for us to find out a term in the partial factor expansion with both these terms together with have a denominator quadratic factor with real coefficients, in which case that can be identified with damped sinusoids in the manner shown here. Now let us continue our discussion with the situation where poles are of multiple order. So far we have considered rational functions where the poles are all simple. So what happens if some poles are of multiple order? In other words, if f of s is Ps over Qs, Qs equals 0 has repeated roots. So some factors are repeated, then we will say that f of s has multiple order poles depending upon the repetition. Suppose it is repeated twice, it is a pole of order 2. If a particular root is repeated 3 times, then we say a pole of order 3. We will illustrate this again by means of an example before we work out give the general rule. Suppose we have f of s equals s plus 2 divided by s times s plus 1 times s plus 3 whole square. So this is an example. We will talk about an example first, then we will give the general rule. Now here we have 3 distinct poles, one at the origin, one at minus 1, and a second order pole at s equals minus 3. Therefore we have k1 over s plus k2 over s plus 1, and corresponding to this multiple order s plus 3 whole squared in the denominator, you can express this as k3s plus k4, or alternately it suits us to have express this as k3 over s plus 3 plus k4 over s plus 3 whole square, because these are easily identified with the Laplace transforms of well-known time functions. So it would be convenient for us to express this in this manner. We can, to streamline this work, to extend this in a general case, we will put it this way. This pole at 3 has got 2 repeated roots, therefore we have k31 and k32. I will put it in this manner, k31 and k32. Now it is to find out k1, we proceed in the same straightforward fashion, multiply this by s and substitute s equals 0. Therefore s plus 2 over s plus 1 times s plus 3 whole squared with the substitution s equals 0, and that gives me value 2 by 9, no problem at all. Similarly, if you want to find k2, you multiply this rational function by s plus 1, which leads me to s plus 2 times s plus 3 whole squared, and substitute s equals minus 1, because that is the pole at which you want to find the residue, and that becomes minus 1/4. So no problem as far as these two are concerned. Now you have to find out k31 and k32. Of this, k32 is easily found out by multiplying this rational function by s plus 3 whole square, so that on substitution s equals minus 3, all the other terms vanish. Therefore k32 can be found out as, or maybe we will put it, we will illustrate this in a more general way. Let us suppose I write here, multiply this s plus 2 over s times s plus 1 times s plus 3 whole squared. I multiply this by s plus 3 whole squared, so that this term will be cancelled out, and we will call this m of s. So, this is m of s, that is, on multiplying this by s plus 3 whole squared, I get m of s. So, on the other side you have k1 s times s plus 3 whole squared plus k2 over s plus 1 times s plus 3 whole squared plus k31 times s plus 1 times s plus 3, sorry, k31 times s plus 3 plus k32. So, on multiplying this by s plus 3 whole squared, the terms corresponding to the partial fraction, each term gets multiplied by s plus 3 whole squared. Now, if you substitute s equals 3 minus 3 in this, you observe that this vanishes, this vanishes, this vanishes, and leaves with you k32. So, k32 is found out again in a straightforward manner by multiplying this by s plus 3 whole squared and substituting s equals minus 3, that will give k32. So, we have found out this residue, and this one. When we have multiple order poles, it is actually the term associated with the linear term that is called the residue. This is really the residue of the pole at s equals minus 3, not this one. In mathematical literature, this is called the residue of the pole at s equals minus 3, and that is the one which is harder to find compared with the others. Now, how do we find k31? Now, the trick in this is we have got m of s is equal to this. Now, suppose you take the derivative of m of s with respect to s, then what happens is this term drops out, and this leaves you with k31. As far as the other terms are concerned, since s plus 3 whole square is a factor here, when you take the derivative of m of s with respect to s, s plus 3 continues to be a factor because it is a quadratic factor. Once you take the derivative, s plus 3 continues to be a factor in both these terms. Therefore, we take dms, the derivative of ms with respect to s, the derivative of m of s with respect to s, equals k1, I'll simply put, suppose I call this as x of s. I have x prime of s plus k31. And now x prime of s has a factor s plus 3. Therefore, you have, when you substitute dms over ds at s equals minus 3 will give me k31. And what is dms, derivative of ms with respect to s? This is after all m of s. So, if you calculate that, you have derivative of m of s with respect to s equals derivative of this s squared plus s times 1 minus s plus 2 times s squared plus s, that is 2s plus 1 divided by s squared plus s, and that is what we have dm of s by s, and s squared plus s whole squared, that is right. So, dms over ds substitution s is equal to minus 3 will give me, after you work this out, with 1 by 36, and that of course is k31. So, the upshot of this is the partial fraction, required partial fraction expansion will be k1 over s, k2 over s plus 1, k31 over s plus 3, and k3 over s plus 3 whole squared, where all the residues are found out. Therefore, f of t will be equal to, corresponding to the first term k1, that is 2 upon 9, 2 upon 9 over s, therefore the inverse Laplace transform is 2 upon 9 times ut. Ut will come at the end anyway. minus 1/4 e power minus t corresponding to this term, and corresponding to k31 you have 1 upon 36 e power minus 3t, and corresponding to k32 over s plus 3 whole squared, k32 is found out as we have not worked it out. K32 will be equal to, when you substitute s equals minus 3 here, k32 is found out as minus 1/6. You can work this out, minus 1/6. Therefore, this becomes minus 1/6, and since it's k32 over s plus 3 whole squared, inverse Laplace transform is t multiplied by e power minus 3t, and the whole thing is multiplied by u of t. So, the final answer is 2 upon 9 minus 1/4 e power minus t plus 1/36 e power minus 3t minus 1/6 t e minus t, t times e power minus 3t multiplied by u of t. That is the final result. Now, after having worked out an example, let us now discuss this in a more general way. When you have multiple order poles, how do you find the various terms in the partial fraction expansion? Let us look at it in a more general way rather than through an example.